I don't know about you, but when you drive, do you look out of the window and look at those undulating sine and cosine curves that pass by and express with awe and wonder how beautiful they are? Now, you're probably wondering what on earth I'm talking about, but actually, so much of life follows a motion of a sine or a cosine curve, or at least has something to do with it, that there is ample fodder for questions for exams. All right, so this whole section, this whole chapter is going to be critically important to those of you doing SACs or exams, because sines and cosine curves can be differentiated, they can be integrated, they can be transformed, they can have algebra applied to them. They can, honestly, there's not very much you can not do to a sine or cosine curve. But let's go back to this undulating stuff. Now, actually, here is a picture of a sine curve. And you might look at it and go, well, all I see is a sine curve, but actually I don't. What do I see? I see hills and valleys, I see rivers, I see constructions, I can see sections where, I don't know, swimming pools can be dug out of gardens, all sorts of stuff, right? So this section here might be a hill, and this here might be a valley. And then suddenly you've got all sorts of, crazy examiners who are going to start asking you questions about heights of hills and, widths of valleys and all sorts of stuff. And that can be done just by considering the sines and cosine curve. So in year 11, you will look to the general form of sines and cosines and tangent graphs, right? So this is very much a quick recap of what you need to know. Right, first things first, there is a sine curve. Now, because of the program I'm using, which is fabulous, otherwise known as Desmos, and so we can have x there or theta. Actually, let's make it theta. Yep. It actually does all of my graphs in radians. Okay, so you're going to probably turn around and go, well, what are all these values? All of those values along there are actually in radians. So worry not. What you need to know is that for a graph of sine, it goes through 0. It has a peak there of pi on 2. It comes back at pi. It goes down there at 3 pi on 2. And the rest of my graph, if it had shown on here, would actually have terminated at 2 pi. Now, sine curves are basically, they go on and on and on. Sinusoidal, they go on and on and on. But they repeat. And so we use this information here to tell us the important parts of the graph. Firstly, it has a period of 2 pi. It means that every time my graph repeats, the distance between the start and the end is 2 pi of a standard sine graph. Now, once we've transformed it, that may change. The maximum value a sine graph gets to is 1, and the minimum value it gets to is -1. Now, again, you actually know why now, because we use the unit circle. Now, if you remember, the values go between 0, pi on 2, pi, 3 pi on 2, and 2 pi. And because it's a unit circle, what is the maximum value that sine and cos ever get to? Well, there's 1, 1, -1, and -1. And that's exactly why, right? The unit circle dictates that the sine curve has a maximum value of 1. So if ever in an exam you get a sine value of bigger than 1, that you try and inverse sine. So if you, for example, had sine theta equals 1.3, and that was in degrees, and you tried to inverse sine that, then you'd be in all sorts of trouble, right? So yeah, you have to be careful. You have to understand what your question is asking you. Actually, let's just rub that out because that looks untidy now. So the maximum, minimum, and then there's this thing here called the amplitude. Now, amplitude is really important because it's the height of the sine curve from the median point to its maximum or minimum. All right, so in this situation, it is 1 unit high, and so we would say the amplitude is 1. Now, great thing to notice is, because the maths is a big fat trick, period and wavelength are interchangeable, right? So they can talk about the period of the graph, they can talk about the wavelength of the graph. Amplitude, really important, is the distance between that mean period and the mean position and the maximum. Here is the cosine curve. So again, the cosine curve has a maximum of 1 and a minimum of -1. We now know this again from the unit circle. Here, it actually has its maximum value at 0. It touches at pi on 2. Minimum at pi, touches again at 3 pi on 2. And again, if I had the rest of this graph, it would fall back down at 2 pi, which would suggest in exactly the same way as the sine curve, the period is pi on 2. So period pi on 2 for a standard cosine curve. Again, if it's transformed, then it will change. You've got the maximum of 1, minimum of 1, and the amplitude, once again, that distance between the median point and the highest point, that distance there, will be what we call the amplitude, right? Now, the cosine curve actually is exactly the same as the sine curve. It's just been translated pi on 2 in the negative x direction, right? If you think about it, yeah, this value here used to be here, and so it has moved the sine curve that way, pi on 2 units, right? And again, that is something that's really, really critically important to know in mathematics. All right, so transformations of sine and cosine curves. Remember, once again, as we've done all the time, we dilate, we reflect, and we translate. Now, dilations can actually happen in 2 ways. They can happen from the x-axis and from the y-axis. Now, dilations from the x-axis are super, super important in maths. Always go back to what your original initial sine curve looks like. Maximum of 1, minimum of -1. 2 pi, pi, and 0. Now, when you are dilating away from the x-axis, you will expect the period to stay the same, so that's why the period does not change, and you have the amplitude will end up doubling or tripling or whatever it is that this dilation is. Really, really important, right? So in this situation here, because I've got an amplitude of 2, I know that my function has been dilated away factor 2 from the x-axis. And how do we show that? Well, as with all other maths, if your original function was sine x, and then you've done a f of x, you've multiplied that whole function by a constant, that is your dilation. And because I've got 2 sine x here, that 2 outside of the function says it's a dilation away from the x-axis. Dilation away from the y-axis, all right? In this situation, when we're moving things horizontally or stretching things horizontally, the amplitude will stay the same, but the period will change. So if we look here, I've drawn the graph of y equals the sine of x on 2. That's exactly the same as the sine of a half of x. My little brain goes, well, if it's inside, it's the opposite of what I'm expecting. So it's not a half, it's actually going to double. Whereby my period used to be 2 pi. I'm going to double it, and that gives me 4 pi, all right? And again, it all comes back down to this standard period of the sine or the cosine curve. As you can see, my maximum and minimum are still 1 and -1, but now my period has changed to 4 pi. When we reflect, again, really helpful to remember the shortcuts. This is what we did at the start of the year. All right, so when you reflect in the x-axis, you replace y with -y, and when you reflect in the y-axis, you replace x with -x. And so what I'm now going to do is I'm now going to take my cosine function, y equals cosine of x, and what normally looks like that is just going to flip. And you can see now, because I'm just reflecting, my maximum and minimum stays the same. My period stays the same. The only thing that changes is the physical form of the graph, right? And that might come in really handy later on. So when we reflect in the y-axis, what do we need to do? Well, basically it's a cosine curve. If we remember our original cosine curve, which does effectively something like that, then when we reflect it this way, what we tend to notice is there's absolutely no difference. Yay! So period stays as 2 pi and the amplitude stays as 1. There's my maximum and there's my minimum, and so my amplitude is 1. Thank you very much. Now, think about the amplitude. If you know what the maximum value is and you know what the minimum value is, then generally you can work out the amplitude. So for example, if I told you that a function had a range, for example, from -2 to 6, you can use that information to find the amplitude, because range is just the difference between the highest value and the lowest value. And where you are using this to describe a sine or a cosine curve, then what do you know? Well, you know that the actual height from the maximum point to the minimum point must be 8 units. How did I do that? 6 minus -2. And then the amplitude would always be half of that, which would be 4. All right, now be careful with the amplitude because context is important. When we reflect in the x-axis, well, you need to be more aware that something is going to happen. Again, let's go back to my standard. This time it's reflecting in the x-axis here. Do reflections change the amplitude? No. Do they change the period? No. So once again, my period is 2 pi, my amplitude is 1. But as you can see, the peaks and troughs actually change. So this used to be the minimum here, and this used to be the maximum. Now, that can become very, very important in terms of exam questions. So try not to get confused. Remember, the way we know it's reflection in the x-axis is, as I've circled here, that minus sign. That minus sign takes my function, all right, so minus my function, using the shortcut tells me that it's a reflection in the x-axis. Now, translations horizontal and vertical, also really, really important. Once again, we need to look at my function here. So what do we have? Cosine of x plus pi on 2. So when I have the cosine of x plus pi on 2, what does this mean? Well, this is my standard function, was the cosine curve, which was this, that would cut through. So what did we decide? That cut through at pi on 2, minimum at pi. There was 3 pi on 2. That was 0. My graph is so out of scale, it's terrifying. This plus pi on 2 means it's going to move it all that way, pi on 2. So that now actually should cross at the point 0, 0. And lo and behold, there it is. Does it change the period? No, because the translation won't change the period. Does it change the amplitude? No, once again, the period is still 2 pi. The amplitude is still 1. But in this situation, what do we notice? Well, we've actually noticed that we have our sine curve, but the sine curve that's reflected. So you could argue here that that's equal to the minus sine of x. Yeah, if you think about it, what does my sine curve normally look like? It looks like this. My minus sine of x would look like this, and that's exactly what we've got. And believe it or not, that's actually an important identity, that the cosine of x plus pi on 2 is equal to the minus sine of x. Finally, another translation, this time a vertically translated, because we've got here, let's really bring it into shape, y is equal to cos x plus 1. This value here merely moves my graph up and down. Now again, remember, this video is just a recap. But every single time I will ask you to make sure that you are aware of what changes when you translate in terms of the period and the amplitude. Now in this situation, although I've moved my graph up by 1, it does not change my amplitude. All right, the only thing that will change my amplitude is the number in front of that cos x or sine x or whatever else, right? This situation, although it's going from 2, it's now going to 0. And if you remember from earlier, just a few minutes earlier, if I do 2 minus 0, that's my maximum minus my minimum, and divide by 2, I still get my amplitude as 1. All that's happened now is my median line effectively has moved up there. Now, don't draw that median line on in any other graphs. You don't need to. I don't want people getting confused for it being an asymptote. I know it might be helpful for you. If you do draw it in to help you get the graph correct, please, please, please make sure that you rub it out afterwards. Okay? Otherwise, we have to mark it. Lastly, graphs of y equals a sine nt and y equals a cos nt. Now, I don't know why they put it this way, because effectively, it could just easily have written a sine nx. Right? For some reason, we express the formula in terms of t. All that means is that's t and that's y. Makes much more sense to me to make it an x. But what it's basically saying is, what actually, when we have graphs in this form, can we see in terms of the period and the amplitude? Well, first things first, this value here is always my amplitude. Okay, so just be aware that that value there is always my amplitude. This n, okay, is going to be some sort of multiplier to change my period. That value is going to change my period. So let's look at a few examples. Here's example 1. When I have y equals sine of x, we know that our period is 2 pi. So if we now compare this to sine of nx, we would see in this situation that n is equal to 1. Okay, that sort of makes sense. For example 2, when I had y equals sine of x on 2, that would be the same as y is equal to, we'll just compare it, y equals sine of nx. In this situation, n would be a half. But when we did this, our period became 4 pi. Well, the only way I know of getting 4 pi, knowing that it's got some sort of a multiplier, is to do 2 pi on a half. If I divide 2 pi by a half, I get 4 pi. All right, so here's example number 3. Again, we'll compare it to y is equal to sine nx. In this situation, n is 2. Right, now, but we know that when we draw this, our period is equal to pi, so it's halved. It's gone from 2 pi to pi, which means I would have to halve it. And there, ladies and gentlemen, is the hint. If I go back and actually say, or compare each of these results here, then what I'm actually doing to get the new period of my function is I'm taking the value of 2 pi, which is my standard period, and dividing it by this multiplier. And again, that sort of makes sense because it's the opposite of what we're doing inside, right? That is really, really important, right? Again, we need to make sure that we express it as a sine nt, where we know that the amplitude is a and the period is 2 pi on n, but this is used ever such a lot in exams, like ever such a lot. Right, here's some examples. What's the period and amplitude for each of these graphs? Right, well, amplitude is the easiest one. It's just 3. And the period, well, what's the value of n? Well, it seems to be 1, although there's a theta there. It doesn't actually matter. You're looking for the value in front of that theta. So the period in this situation is, what's the period? 2 pi on 1, so it's 2 pi. Fabulous. What about this one? All right, amplitude in this situation is a half, and the period, well, what's the value in front of the theta? Once again, it's a 1, so my period would stay as 2 pi. This one here, slightly more tricky. Amplitude is equal to 2. Period in this situation, sine curve, standard, 2 pi, divided by 2/3. Now, I'm going to write this out longhand because lots of people don't know how to do this division stuff. So when I go back to junior school, I know that we keep, we change, and we flip. 2's cancel there. And so I find out that my period becomes 3 pi. All right. This is critically important for the VCAR exams and any exams you need to do. Now, obviously you're going to be asked to sketch these things. So here is an example of a sketch that you might be asked to do. 5 cos 3x, and you have to draw it between 0 and pi. First things first, always consider the original graph. Sketch the original, and then my view is recalculate using each of those transformations. Finally, sketch it. So if we look over, if we scroll below, we've got 5 cos 3x. Okie dokie. So here we go. My original cosine curve looks like this, with 1 and minus 1. All right. That 5 means I can now change that to 5 and minus 5. Awesome. 3x. Got to rework out the period because the period is going to change. So the period of a standard cosine curve was 2 pi. Divided by the value of n is 2 pi on 3. Am I translating it? No, I'm not. So this value here stays as 0. This value here now is 2 pi on 3, comma 5. So there's 2 pi on 3. Wow, how do I work out all my other values? Well, normally for a standard cosine curve, it would cross through at pi on 2, pi, and 3 pi on 2. Now, because this 3 is basically squidging all of my graph by 1/3, I now know that all of these values would have to be squidged by 1/3 as well. Alternatively, multiply them by 1/3. So I now can write straight away that that becomes pi on 2, which becomes pi on 6. This value here becomes pi on 3. And this value here, which was 3 pi on 2, multiply that by 1/3, gives me pi on 2. And that would be 0. There you go. There is my sketch. I need to make sure that I label the important points. So if you go back to what I've originally drawn here, because it's been limited, because the domain's been limited, you have to do the circles at the start and the end, either filled or unfilled. Now in this situation, they'll be filled because it includes 0 and pi. I'm going to write on my coordinates of 0, 5, my pi, minus 5. All right, now, hold on a moment. That's weird. I didn't finish my graph off. No, I didn't. And obviously, in this situation, we needed to go between 0 and pi. Now, because this isn't pi, I actually needed to continue my graph for as long as it actually needed to go. Well, how would I have done that? I know, all I've got here is this 2 pi on 3 business. I don't know where the rest of the graph is. Well, actually, yes, you do. Remember, everything now will repeat. Every coordinate position I have will repeat by 2 pi on 3. So I've got pi on 6, and I'm going to add 2 pi on 3, which is 4 pi on 6. So that now, this value here now becomes 5 pi on 6. This value here, pi on 3, I'm going to add 2 pi on 3, which gives me 3 pi on 3, which is pi. And so here is my final value of pi. And it just so happens to coincide with the end of where I wanted my graph to be. These points here, maximums and minimums, if they're easy to find, and this point of the course probably not, then by all means you can find them and have to put them on. But I think pretty much that is going to be the end of this lesson here. So we've looked at the basics for sine and cosine graphs. It was a pretty much repeat of year 11, but we're now looking at some transformations as well. All right, well, thanks very much for watching. I look forward to seeing you next time. Thanks for joining us for that video. It was really good having you. Now, if you'd like to know when the next video is coming, why not click on subscribe? Alternatively, head on over to MaffsGuru.com where you can watch all of the videos on its own dedicated website. While otherwise, watch the video that's just popped up. It'll be part of this series. All right, take care. See you again soon.